November 1944, Manchuria, a Boeing B-29 Superfortress, tail number 42-6358, sits motionless on frozen ground near the Soviet border. Its aluminum skin gleams under pale winter light. The aircraft is intact. The engines are cold. No battle damage mars its surface. This bomber didn't fall from the sky in combat. It landed. And now, Japanese engineers stand before it with notebooks, calipers, and a singular mandate from Tokyo. Understand everything. The B-29 represented the apex of American industrial ambition. 4 Wright R-3350 Cyclone engines, each delivering 2,200 horsepower, a wingspan of 141 feet, pressurized crew compartments that allowed men to operate at altitudes where the air was too thin to breathe, remote-controlled gun turrets, a bomb capacity of 20,000 pounds, maximum speed 357 miles per hour, service ceiling 31,850 feet. These were not just specifications, they were a declaration. No fighter in the Japanese arsenal could reach it. No anti-aircraft gun could touch it. The B-29 flew above the war. The aircraft in Manchuria had departed from a base in China on a mission against the Japanese home islands. Engine failure forced the crew to divert. They chose Soviet territory. The USSR and Japan were not yet at war. The crew interned. The aircraft remained. And through backroom agreements between Moscow and Tokyo, the bomber became a prize. Japan's aviation industry had been world-class a decade earlier. The Mitsubishi A6M0 dominated the Pacific in 1941 and 1942. Fast, maneuverable, lethal in the hands of veteran pilots. But the Zero was a fighter, light, fragile, built for dogfighting, not for endurance or altitude. By 1944, Japan's industrial base was fracturing under blockade. Aluminum was scarce. Fuel reserves dwindled. Experienced pilots were dead. And now, American bombers operated from bases beyond reach, delivering incendiaries and high explosives with impunity. The B-29 arrived in Japan by rail and barge, disassembled into sections. Engineers from Nakajima Aircraft Company, Kawasaki Heavy Industries, and Mitsubishi Heavy Industries gathered at a secure facility outside Tokyo. Security was absolute. Photography was forbidden except for technical documentation. Every component would be measured. Every system would be diagrammed. If Japan could replicate even a fraction of this machine's capability, it might extend the war. It might force negotiations. It might buy time. They began with the airframe. American engineers had used a semi-monocoque structure, aluminum alloy skin riveted to internal stringers and formers. The skin itself bore load. This reduced weight without sacrificing strength. Japanese bombers used heavier internal frameworks with fabric or thin metal covering. The difference was profound. The B-29's fuselage was both lighter and stronger. The riveting technique was unfamiliar. American factories used flush rivets on critical surfaces to reduce drag. Japanese standard practice relied on protruding rivets. The time required to countersink and install flush rivets was prohibitive in Japanese production schedules. But the Americans had done it. Thousands of rivets per aircraft, precision at scale. The engineers documented everything: dimensions, alloys, rivet spacing, skin thickness. They photographed joints and measured stresses. One engineer noted in his report that the tolerances were tighter than anything produced domestically. Gaps between panels measured in fractions of a millimeter. Surface finish was smooth. Drag was minimized. This was not accidental. This was systematic. The aluminum itself told a story. The alloy was 24ST, a designation that meant nothing to most of the team initially. Research revealed it was an aluminum-copper alloy with magnesium and manganese additions. Heat-treated to specific temperatures, age-hardened through controlled cooling. The result was metal that combined strength with workability. Japanese aluminum supplies were inconsistent. Quality varied between batches. Impurities weakened the material. The Americans had standardized their metallurgy. Every sheet met specifications. Every rivet matched its hole. The supply chain delivered reliability. They measured wing loading. The B-29 carried 69 pounds per square foot. Japanese heavy bombers averaged 50 to 55. Higher wing loading meant higher speeds but required longer runways. The Americans had built those runways on islands across the Pacific. Engineers, construction battalions, heavy equipment, runways appeared where there had been jungle or coral. The B-29 needed infrastructure. America provided it. Then came the engines. The Wright R3350 Cyclone was an 18-cylinder, twin-row radial. Displacement, 33,336 cubic inches. Compression ratio, 6.85 to 1. Equipped with 2 General Electric turbochargers per engine. The turbochargers were the revelation. Exhaust gases spun turbines that compressed intake air, maintaining sea-level pressure at altitude. This allowed the engines to produce full power above 30,000 feet. Japanese aircraft used mechanical superchargers, which drained power from the engine to operate. The turbocharger was free energy, harvested from waste. Disassembling the first engine took a week. Each component was logged: bearings, pistons, crankshaft, valve train. The metallurgy was extraordinary. American steel alloys contained elements Japanese industry could not source in sufficient quantity: nickel, molybdenum, chromium. These materials gave the engines heat resistance and strength. The Japanese substitutes were inferior. Engines built with available alloys failed sooner, ran hotter, delivered less power. One engineer, a specialist in propulsion systems, wrote in a private letter that became part of the post-war record, "We are not behind by years. We are behind by decades in industrial capacity and material science." The turbochargers alone were beyond replication. The turbine blades had to withstand exhaust temperatures exceeding 1,000 degrees Fahrenheit while spinning at tens of thousands of revolutions per minute. Japanese metallurgy could not produce blades that survived these conditions. Prototype turbines cracked, disintegrated, killed test pilots. The Americans had solved this problem. The solution was not in the design alone. It was in the materials, in the supply chain, in the industrial ecosystem that could produce such materials in quantity. The engine cylinders were forged, not cast. Forging aligned the metal's grain structure, increasing strength. Japanese engines used castings, faster to produce, cheaper, weaker. The Americans had invested in forging presses, heavy industrial equipment, infrastructure. The cylinders showed no porosity, no defects. Quality control was rigorous. Fuel injection systems used precision-machined components. Injector nozzles drilled to exact diameters. Too small and fuel flow choked. Too large and mixture ratios failed. The tolerances were measured in thousandths of an inch. Japanese machine tools could not hold such precision reliably. American tools could. Mass production with precision was the American advantage, not one perfect engine. Thousands of identical engines, all meeting specifications. The propellers were Hamilton Standard Constant Speed units, 4 blades per propeller, hydraulic pitch control. The pilot set desired RPM. The propeller adjusted blade angle automatically to maintain it. This optimized efficiency across flight conditions. Japanese propellers were simpler, 2 or 3 blades, manual pitch adjustment. Pilots managed engine speed and propeller pitch separately. Workload increased, efficiency decreased. Next, the pressurization system. The B-29 was the first operational bomber with a pressurized cabin. Crew members operated in shirt sleeves at altitudes where unprotected men would lose consciousness in seconds. The system maintained cabin pressure equivalent to 8,000 feet while the aircraft flew at 30,000. This required pumps, seals, valves, and regulators of extraordinary precision. Leaks were catastrophic. A single failed seal could depressurize the entire cabin. The Americans had engineered redundancy. Multiple pumps, backup systems, automatic controls. Japanese engineers tested the pumps, disassembled the valves, studied the seals, rubber compounds, gasket materials. Everything was specified to tolerances they could measure but not replicate. The gap was not in understanding. It was in execution. Japan lacked the industrial depth to manufacture these components reliably. The cabin was divided into 3 pressurized sections: forward compartment for pilots, bombardier, and navigator; central compartment for gunners; rear compartment for tail gunner. Connecting tunnels ran above the bomb bays. Unpressurized. Crew crawled through these tunnels wearing oxygen masks when moving between sections during flight. The design was practical, complex. It required pressure bulkheads, sealed hatches, pass-through connections for control cables, and wiring that maintained pressure integrity. The engineering was obsessive. Every rivet hole in a pressure bulkhead was a potential leak. American engineers had developed sealants, synthetic rubber compounds that remained flexible at temperature extremes. Japanese sealants hardened in cold, cracked, failed. The Americans had solved problems Japanese engineers were still discovering. The defensive armament was next. 12 Browning M, 250 caliber machine guns mounted in 5 turrets. 4 turrets were remote controlled. Gunners sat in pressurized compartments, aiming via periscopes and analog computers that calculated lead and deflection. The system was electromechanical: gears, servos, feedback loops. When a gunner moved his control stick, electric motors rotated the turret. The guns followed. The computers adjusted for airspeed, target speed, and range. This was automation. This was fire control as a system, not as individual skill. The analog computers were marvels. Mechanical calculators built from cams, gears, and differential mechanisms. They solved ballistics equations in real time. Japanese gun sights were optical, manual. They relied on the gunner's experience and judgment. The B-29 system made every gunner competent. It multiplied effectiveness. One engineer noted that even mediocre crews could achieve hits at ranges that would challenge Japanese aces. Each turret had its own power supply, its own control circuit. Failure of one turret did not compromise others. The design philosophy was evident: redundancy, isolation, survivability. Battle damage could destroy a turret. The bomber fought on. Japanese aircraft concentrated systems. One hit could cascade into total failure. The ammunition feed systems used electric motors and mechanical linkages. Belts fed from storage boxes. Spent casings ejected overboard. The guns could fire continuously for extended periods. Cooling was passive. Airflow at altitude. Japanese fighters often carried limited ammunition. 20 seconds of fire time. Conservation was mandatory. The B-29 carried thousands of rounds per gun. Suppressive fire was doctrine. Then the instruments. American cockpits were dense with gauges and indicators, altimeters, airspeed indicators, engine monitors, fuel flow meters, hydraulic pressure, electrical load. Every system had a gauge. Every gauge was readable in low light. The layout was logical. Pilots could scan instruments in sequence without searching. Japanese cockpits were simpler, fewer instruments, less information. Pilots flew by feel and experience. The American approach was data-driven. Trust the instruments, monitor the systems, maintain awareness. The altimeters were sensitive, readable to 100 feet. Japanese altimeters were cruder. Accuracy mattered less in low-altitude operations, but the B-29 operated at extremes: 30,000 feet. Precision navigation, bombing accuracy depended on knowing exact altitude. The instruments provided that precision. Engine instruments showed cylinder head temperatures for each engine, oil pressure, oil temperature, fuel pressure, manifold pressure, RPM exhaust temperature. The pilot and flight engineer monitored 14 parameters per engine, 56 data points for propulsion alone. Early detection prevented failures. Japanese bombers had basic engine instruments. Failures often came without warning. The electrical system was extensive: generators on each engine, batteries, distribution panels, wiring harnesses. The B-29 carried more electrical capacity than many Japanese fighters weighed. Radios, navigation equipment, autopilot, bomb release systems all required power. The wiring was color-coded, organized, serviceable. Japanese aircraft used minimal wiring, often bundled without clear identification. Repairs were difficult. Failures were frequent. Circuit breakers protected every electrical circuit. Overload tripped the breaker. The system isolated the fault. Power continued to other systems. Japanese aircraft used fuses. One failure required replacement, often in flight, in combat. The Americans had engineered maintainability into every system. The radio equipment was sophisticated. Command radio, liaison radio, interphone for crew communication, radio compass for navigation, identification friend or foe transponder. The radios used vacuum tubes, reliable, serviceable. Japanese radios were less reliable. Vacuum tubes were in short supply. Quality was inconsistent. The autopilot was a revelation. The Honeywell C1 system could hold heading, altitude, and airspeed. Pilots engaged the autopilot during long overwater flights. Fatigue decreased. Accuracy improved. The system used gyroscopes, servos, and feedback loops. It sensed deviations and corrected them. Japanese bombers had no autopilot. Pilots hand flew every mile. Exhaustion was inevitable. The landing gear was robust. Dual main wheels on each side, designed for heavy loads and rough fields. The hydraulic system that retracted the gear was smooth, reliable. Japanese bombers often used manual or partially manual systems. Crews cranked wheels by hand. The B-29's gear folded into the wings and fuselage with the press of a lever. Time saved. Pilot workload reduced. Brake systems used hydraulic pressure, independent brakes for each main wheel. Differential braking assisted in ground handling. The brakes could stop a loaded bomber in reasonable distances. Japanese bombers had cable-operated brakes. Less effective. Longer stopping distances. Runway accidents were common. They studied the bomb bay. 2 bays, fore and aft. Doors operated by electric motors. Bomb racks held ordnance of various sizes. Release mechanisms were electrically triggered from the bombardier station. The Americans had standardized. Bombs of different weights used the same attachment points. Loading was fast. Turnaround time between missions was minimal. Japanese bombers required manual loading. Mission preparation took hours. The bombardier station contained the Norden bomb sight, a precision optical mechanical device. The bombardier input altitude, airspeed, wind speed, and target data. The sight calculated the release point. During the bombing run, the sight was linked to the autopilot. The bombardier controlled the aircraft. Minor corrections, the sight adjusted. At the computed moment, bombs released. Accuracy was measured in hundreds of feet from high altitude. Japanese bomb sights were simpler. Manual calculations, estimation, accuracy was measured in thousands of feet. Even the paint was different. American bombers used primer and topcoat systems that resisted corrosion. Aircraft operating over salt water faced constant oxidation. Japanese paint systems were thinner, less protective. Corrosion was endemic. Maintenance hours increased. Service life decreased. The Americans had engineered durability into every layer. The paint contained zinc chromate, a corrosion inhibitor. It gave the primer its distinctive yellow-green color. Japanese primers lacked such additives. Aluminum corroded. Structural integrity degraded. The Americans understood that aircraft fought not just enemies but environments, salt, humidity, temperature extremes. Every material choice reflected this understanding. By early 1945, the analysis was complete. Reports filled cabinets. Engineers had documented thousands of components. The conclusion was unavoidable. The B-29 was not one innovation. It was a system of systems. Each subsystem depended on materials, processes, and manufacturing capabilities that Japan did not possess. Replication was impossible. Not because Japanese engineers lacked skill, because Japanese industry lacked capacity. The reports went to military leadership, to industrial ministers, to the Prime Minister's office. They were read, filed. The information changed nothing. Japan was committed. Surrender was unthinkable. The war would continue until circumstances forced an end. Nakajima attempted to produce a Japanese equivalent, the Nakajima G-10N Fugaku, a six-engine heavy bomber designed to reach the United States. It never flew. Prototypes were never completed. The engines were unavailable. The materials were unavailable. The manufacturing capacity was unavailable. The Fugaku existed on paper. The B-29 existed in the thousands. Boeing produced nearly 4,000 B-29s between 1943 and 1945. 4 factories, thousands of subcontractors, millions of man-hours. An assembly line in Wichita completed 1 bomber every 4 hours at peak production. Japan could not match this, not remotely. The industrial disparity was total. The Boeing plant in Wichita covered over 2 million square feet, 16,000 workers per shift, 3 shifts per day. The assembly process was choreographed. Components arrived from suppliers. Subassemblies moved through stations. Wings attached, engines mounted, systems installed, final inspection, test flight, delivery. The entire process from raw materials to operational aircraft took months. But the output was continuous, relentless, overwhelming. Japanese aircraft production peaked at 28,000 units in 1944. All types, fighters, bombers, trainers, transports. The United States produced 96,000 aircraft that year. The B-29 alone represented 4% of Japanese total production capacity applied to a single model. The scale was incomprehensible. The engineers who studied the B-29 understood this. Their reports were technical, precise, unsentimental. But between the lines, a recognition emerged. The war was not being lost in the skies over Tokyo. It was lost in factories in Seattle, Wichita, and Renton. It was lost in steel mills and aluminum smelters, in supply chains that stretched across a continent, in an industrial base that could build 4,000 advanced bombers while also producing fighters, transports, tanks, ships, and trucks. One report, submitted in February 1945, concluded with a single line that summarized the strategic reality. The aircraft represents a level of integration between design and production that our industry cannot achieve under current conditions. The phrase "current conditions" was optimistic. It implied that given time, given resources, Japanese industry might close the gap. The engineers knew better. The gap was not a matter of years. It was generational. American industrial capacity was built over decades. Universities, technical schools, machine tool industries, steel production, chemical industries, electrical manufacturing. Each sector supported the others. The ecosystem was mature, self-reinforcing. Japan had built impressive capabilities in specific areas. But the breadth was missing. The depth was missing. By March, B-29s were flying from bases in the Mariana Islands, 1,500 miles from Tokyo, within range. They came in waves, hundreds at a time. Incendiaries fell on cities built from wood and paper. Firestorms consumed square miles in hours. The bombers flew too high for interceptors, too fast for flak. Losses were minimal. Missions continued nightly. Japanese fighters tried to intercept. Pilots pushed their aircraft to the limits, climbing to altitude, straining engines. Some reached the bombers. Attacks were desperate, head-on passes, ramming attempts. The remote-controlled turrets tracked them. 50 caliber rounds found targets. Fighters fell. The bombers continued. One pilot, Lieutenant Sadao Takai, recorded his experience in a diary recovered after the war. He described climbing to 28,000 feet in his Kawasaki Ki-61. The engine overheated. Performance degraded. He saw the bombers above him, unreachable. He dove, returned to base, fuel exhausted. Months later, he was killed attempting another intercept. His diary ended with the observation that the war was being fought at altitudes Japanese fighters could not sustain. In August, 2 B-29s carried atomic weapons, Hiroshima on the 6th, Nagasaki on the 9th. The bomber that had been disassembled in a hangar near Tokyo had siblings that ended the war. The aircraft that dropped the Hiroshima bomb was named Enola Gay. Tail number 44-86292. Pilot Colonel Paul Tibbets. The bomb, codenamed Little Boy, weighed 9,700 pounds. The aircraft flew at 31,000 feet. The bomb detonated at 1,900 feet above the target. Yield, 15 kilotons, 70,000 dead. The city center ceased to exist. 3 days later, Boxcar carried the Nagasaki bomb. Fat Man. Plutonium implosion design, 21 kilotons, 40,000 dead. Japan surrendered on August 15th. The B-29 had delivered victory. Not through attrition, through annihilation. After the surrender, American occupation forces recovered the reports. Engineers who had studied the captured B-29 were interviewed. Some emigrated. Some joined post-war Japanese aviation firms. Their knowledge contributed to Japan's transformation into an industrial power in the decades that followed. The lessons were absorbed, not the specific technologies of 1944, but the principles. Integration, precision, systems thinking, scalability. The B-29 that landed in Manchuria was eventually scrapped, its components dispersed, but the education it provided endured. Engineers who measured its rivets and tested its pumps carried that knowledge forward. Post-war Japanese manufacturing became synonymous with quality and precision. The roots of that reputation trace, in part, to a winter day in 1944, when men with notebooks stood before an aluminum giant and confronted the gap between ambition and capability. Toyota adopted American manufacturing techniques, quality control, continuous improvement, just-in-time production. The principles came from American industrial engineers who occupied Japan. Those engineers had learned their trade in the factories that built the B-29. The knowledge transfer was direct, deliberate, transformative. Sony emerged from the ruins, Mitsubishi rebuilt, Kawasaki diversified. Japanese engineers applied the lessons, not to building bombers, to building products, electronics, automobiles, machinery. The focus shifted from military to civilian. The standards remained: precision, reliability, integration. By the 1970s, Japanese manufacturing led the world in quality. American industries faced competition they had not anticipated. The students had become masters. The transformation was complete. Wars are decided by production as much as by courage. The B-29 was not invincible. It was manufactured at scale. That distinction mattered. It mattered when bombs fell. It mattered when cities burned. It mattered when engineers filed their reports and acknowledged that replication was beyond reach. The bomber was not 20 years ahead because of a single breakthrough. It was 20 years ahead because every component represented a mature industrial system. Hundreds of suppliers, thousands of workers, decades of investment in materials, science, manufacturing technique, and quality control. The aircraft was a symptom. The cause was deeper, broader, more fundamental. Japanese engineers saw this. They documented it, they reported it, and they understood that the war they were analyzing was already over. The question was never whether Japan could build a B-29. The question was whether Japan could build the industries that made the B-29 possible. In 1944, the answer was no. The frozen morning in Manchuria when the bomber arrived marked the beginning of that understanding. The reports that followed marked its acceptance, and the decades after the war marked Japan's response, not by replicating the past, but by learning its lessons. Precision became doctrine, integration became method, systems thinking became culture. The B-29 flew into history. Its children and grandchildren became airliners, carrying passengers across oceans in pressurized comfort. The Boeing 377 Stratocruiser used B-29 wings and engines. The 707 traced its lineage to lessons learned: pressurization, systems integration, reliability. The commercial aviation industry was built on foundations the B-29 established. The turbochargers evolved into turbojets. General Electric, which built the B-29's turbochargers, developed the first American jet engines, the J-31, the J-33. The technology path was direct. Exhaust-driven turbines became gas turbines, propellers disappeared, jets replaced them. The B-29 was a bridge, piston to jet, propeller to turbine, the transition generation. The manufacturing techniques spread across industries, precision metalwork, quality control, systems engineering. These were not aviation-specific, they were universal. Automotive industries adopted them. Consumer electronics, appliances. The B-29's legacy extended far beyond aviation. The story is not about a single machine. It is about the distance between what is possible and what is achievable. That distance is measured in factories, in supply chains, in education systems, and in the decades required to build them. The engineers in that hangar understood this. Their reports made it clear. The bomber before them was not an enemy, it was a mirror. And the reflection showed them where they stood and how far they had to go. Numbers tell the story. 4,000 bombers, millions of rivets, thousands of suppliers, decades of investment, one captured aircraft, one analysis, one conclusion. The gap was unbridgeable in time to matter. That conclusion echoed long after the war ended. It shaped post-war policy. It influenced industrial strategy. It guided educational reform. Japan rebuilt not by denying the gap, but by acknowledging it and working systematically to close it. The effort took generations, but it succeeded. The engineers who stood in that hangar in 1944 could not have imagined what their nation would become. They saw only the gap, the impossibility, the overwhelming superiority of American industry. But they documented what they saw. They preserved the knowledge. And when the war ended, that knowledge became foundation. The B-29 was a teacher. Its lessons were harsh, but they were learned. And in learning them, Japan transformed from a defeated power into an industrial leader. The aircraft that represented insurmountable advantage became a catalyst for change, not through imitation, but through inspiration, not by copying, but by understanding. The bomber is gone, the engineers are gone, but the legacy persists in every precision-manufactured product, in every quality-controlled process, in every integrated system. The ghost of that silver aircraft sitting on frozen ground in Manchuria haunts modern manufacturing. Its lessons, learned in desperation and defeat, built the prosperity that followed. That is the story the numbers tell. That is the legacy the engineers documented. That is the truth the bomber revealed. Wars are won in factories long before they are fought in the field.